So let's look at the notation. One of the things that's important to understand here is the notation. And if we have the limit of a function f, lim x approaches c of f of x. Okay, that's how the way you would read that is the limit as x approaches c of f of x.
Oh, I remember this.
Okay?
On to memories.
Good.
Okay. Cool.
Now, your limit is always going to be a value of y. Okay? That's what we're trying to find. What's the value of y as x is getting really close to a particular value? If we were looking at this function here, the parent function x squared, and then it's plus 3, so it's just the parent function x squared, moved up 3. And if we want to find the limit of this function as x approaches 2, okay, we would say the limit as x approaches 2 of x squared plus 3. That's how we would read that. And you can see here in green, as we approach from the left and we approach from the right, we're approaching where x equals 2. The value of our function is on both sides is getting closer and closer and closer to 7. And that's the limit, okay? Now, in this particular instance, it happens to be the point on that function, the point 2, 7. And we're going to look in a minute at when can we just plug it in and evaluate, okay? But you can also see here, we could use a table, and you'll notice I started at 1.94, and this would be approaching from the left, and on the bottom here would be like we're approaching from the right, okay, where x is coming from the right or x is coming from the left. And you'll notice as x is getting closer and closer to 2, the value of x starts below 7 and is getting the value of y starts below 7 and is getting closer and closer to the actual value of 7. Okay? Here, as we start off to the right at 2.06, and then we come back towards 2 from the right, we were above 7, and now it's decreasing, decreasing, approaching 7. Okay? So you'll notice we're approaching 7 as we come from the left and as we come towards 2 from the right.
So you have to be coming from both directions?
Yes. It has to approach, and we're going to mention this in just a sec, it has to be approaching the same value from both directions. Okay? Now, we're talking about coming from the left and coming from the right. We actually have what are known as left-hand limits and right-hand limits. Okay? The left-hand limit, notice we said it was from each side. So as we're coming from the left side, the limit as x approaches c from values that are less than c, or to the left of c on our x-axis, we would write like this. The limit as x approaches c, and you put a little negative after it. Okay? That means we are approaching this value from the left. Okay? So, for example, on our last one, I could have put the limit as x approaches 2 from the left side. And then we have the right-hand limit as well. If we're approaching from values that are greater than c, we put the little plus sign after the c. So, for example, we could have written the limit as x approaches 2 from the right. Now, I want you to see kind of how this works. Okay? And for this, I'm going to actually jump to this example down here. Okay? Here we have a piecewise function. This function f is defined as x squared minus 4 when x is less than or equal to 2. So you'll notice here's the entire parabola, x squared minus 4. But we only want that parabola when we are less than or equal to 2. So this is part of the function f. Okay? Once we pass 2, we want to jump to the line 1/2 x plus 1. So you can see here, it jumps up to that point and continues on once we pass 2. All right? So, here we have the limit as x approaches 2 from the left. All right? So as I come from the left-hand side, okay, as I'm coming from this side, the value of my function is way up here, then it comes down, then it hits 0 at -2, then it hits -4, and it's coming back up. And what is the value of my function approaching? Well, that's what x is approaching. What's the function approaching? 0. Okay? The function is approaching 0. Okay? Here we're at -4, then somewhere in here we're at -3, -2, -1, and it's getting closer and closer to 0. Okay? Now, from the right-hand side, as x gets closer to 2 from the right-hand side, what's the value of my function approaching? 2. Okay? It's not approaching 0, it's approaching 2. It doesn't actually equal 2, but it's approaching 2. So I would say my limit, my right-hand limit, equals 2. Okay? Does that make sense? Okay. Which part? Well, you have to approach from the left and then approach from the right. I know typically, but for limits, when you're looking at a left-hand limit, you would look at it coming from the left, and for a right-hand limit, you have to start to the right and come back towards it from the right side. Okay? Now, this one kind of throws us for a little bit of a loop because we're approaching 2 different values. All right? So, my left-hand limit exists, it equals 0. My right-hand limit exists, it equals 2. But if I were just asking for the limit as x approaches 2, what would I have to say? What do you think? Okay? We're actually not going to have a limit. The limit, we would say, does not exist. Okay? And the reason is, remember what a limit is. The limit is a value, singular, that the function approaches. Here, the function is not approaching a single value. It's approaching 2 different values. Okay? So because it's approaching 2 different values, there isn't one value that it's approaching, so the limit doesn't exist. Okay? And that actually brings us to one rule here that we have for limits. to it. Okay? In answering the question, does a limit exist as x approaches a specific value? Well, there's basically a three-part test. Does a limit exist? First of all, the left-hand limit must exist. We have to be approaching something as we come from the left. Secondly, the right-hand limit has to exist. And then finally, the left and right-hand limits have to be equal. This is the part that the example we just looked at failed. Okay? One side was approaching 0, the other side was approaching 2. So while both left and right-hand limits existed, they weren't equal, so the limit didn't exist. Okay? Now let's take a look at a couple other examples of some cases that we might run into. All right? One of these is going to be, say, the radical function. Okay? Okay? The radical function. Here's our parent function, square root of x. Okay? As I come from the right side here, what value is my function approaching? What? 0. Okay? So my right-hand limit of the square root of x as x approaches 0 is 0. However, what do you notice about our function on the left? On the left of 0, there is no function. It's not even defined down here. So I can't approach it from the left, can I? Therefore, my left-hand limit does not exist. Now, since this doesn't exist, we automatically now know this does not exist. Okay? Because both of these would have to exist and be equal. Okay? So the limit doesn't exist because the left-hand limit doesn't exist. Okay? Another case that we can look at, we'll finally get to this one here, I need to reorder these, is the reciprocal function. Okay? You see this happen with functions a lot, not just reciprocals, but notice we want the limit as x approaches 0. Okay? Now I told you it doesn't have to be defined at that point. Here the function is not defined at 0, but what happens as we approach from the left-hand side? Our function approaches
0.
Our function approaches what from the left-hand side? As we get closer to 0, negative infinity. Okay? Now, there are two schools of thought, and both of them are valid. Okay? And actually on the AP, sometimes on the multiple choice, they actually give you one of these, and some they give you the other. All right? Both are valid answers. Okay? But you could either say it's approaching negative infinity, or technically speaking, the better answer would actually be does not exist. Technically, the limit has to approach a value. And since infinity is not a value, they say it doesn't exist. Okay? Either one is fine, but just be aware. Especially if you look at other stuff online.
There's no preference for the IB?
Not that I've seen. Yeah. And that's kind of across the whole mathematical community. Honestly, I never learned it as doesn't exist. Everywhere I had learned it, it was always negative infinity. And from the right-hand side, it's going to positive infinity. Okay? Or we could say it does not exist.
So,
I had always learned it this way.
It provides more
But-
information.
It does. It does provide a little more information. It's a little more useful. But either way, though,
doesn't exist.
the limit as x approaches 0 does not exist. Even if you look at it in terms of negative infinity and positive infinity, the limit would not exist. Okay?
You get the same answer, so.
You'll get the same final answer, yeah, either way. Okay? All right. So now, there's a question that kind of comes up here. You know, we saw our first example, and hey, it ended up being an actual point on the graph. We could have just plugged in 2 and figured out it was 7, right?
Can you not always do that?
Well, that's what we're kind of addressing here. Here's another one where the limit as we approach 2 from the left is 0. The limit as we approach 2 from the right is 0. So the limit as x approaches 2 is 0. That's the same thing we would have gotten if we would have plugged in 0. It's in this range here, so we would have had to plug it in there. 0 squared, or 2 squared minus 4 is 0. Okay, we could have just evaluated that. So the question becomes then, when can we just evaluate the function, and when do we have to use some other method, like a table or looking at the graph or something like that? Okay, and the answer is this, okay? If a function is continuous around the value that x is approaching, then we can find the limit simply by evaluating the function there. So it's got to be continuous.
So it can't be piecewise.
Well, here's the thing. We looked at 2 different piecewise functions, right? We looked at this case where there was a jump. So that's not continuous. And here, if we had just tried to evaluate, we would have gotten a wrong answer. We would have gotten 0 when, in fact, the limit doesn't exist. Here, however, we had a piecewise function, and notice the 2 pieces meet. So it is continuous about the value of 2. All right? Since it's continuous there, we could have just plugged in 2 and gotten our limit. Okay? So that's kind of the key there. If a function is continuous around the value, it doesn't have to be real far around, just around the value, then we can evaluate. Here's an example. Okay? We have this rational function, f of x equals x squared plus 3x plus 2 over 13x plus 8. Our domain, x can't be negative 8/13. And you can see here, that's what that function would look like. It actually has a slant asymptote and a vertical asymptote. Okay? So if I were to ask you, hey, what's the limit as x approaches 4? Well, 4 is right here. Am I continuous around 4? Yeah. So can I just plug it in? Yeah. And I'll get 60 over 30, or sorry, no, other way around. 30 over 60, which is 1/2. The limit's 1/2. Okay? If, however, I was asked to find the limit as x approached negative 8/13, I see, wait, it's not defined at negative 8/13, so I need to figure out a different way of finding the limit. And that's when I might graph it, or I might use a table, and I recognize, hey, it's approaching negative infinity from the left, positive infinity from the right, so the limit does not exist. Okay? So that's the basic rule for when you can evaluate. It's got to be continuous around the value of x you're approaching. All right, anyone have any questions about limits in general? Keep that in mind as you do a little bit of practice. Okay? Some of these you can just plug it in and evaluate. Others you can't. Okay? So, all right.